Hello, my name is Ian Sierra, and this is the Lab 4 video report. The purpose of this lab is to examine the motion of a spring mass system where the mass swings in an arc while it oscillates on a spring. The motion will be analyzed in Tracker. We will need to compare the predicted and observed motion of the mass and apply energy changes computed in the model. The computations will require us to use concepts and formulas that we have learned in the video lectures, including Newton's second law, Hooke's law, the energy principle, and the period formula. In Tracker, I had to set up the length scale to be 0.7 meters. The coordinate axis is set up where the origin is at the attachment point and the axis is aligned with the y-axis. The point mass was analyzed to generate the graph. The video starts where the mass is just about to be released and goes all the way to the end of the video, and as a result, this oscillating graph is generated, which has x and y coordinates. And these x and y coordinates are plotted in a separate spreadsheet that will be used when we create our computer model. Calculations for spring stiffness and relaxed length are needed to be made in order to set up the computer model. The mass and acceleration due to gravity are specified and needed for the computations. The spring stiffness was calculated from the period formula, as you see on the screen. The period was found by counting the troughs in the graph and Tracker and dividing the time by the number of troughs. Spring stiffness is calculated to be 7.02 newtons per meter. Relaxed length was calculated by setting the spring force equation, which is Hooke's law, equal to the gravitational force equation and rearranging the formula to solve for L naught, which is 0.14 meters. The initial position, which was taken from the initial y position in Tracker, and the initial velocity. I also had to specify the acceleration due to gravity and the calculated values of the spring constant or spring stiffness and the relaxed length of the spring. The proper formulas for L hat, and S, which is the stretch, are all written and needed for the spring force. In the next few lines, the formulas for kinetic energy, gravitational potential energy, spring potential energy, and total energy are all written, which all stem from the energy principle and will be needed for the loop. In the motion prediction calculation loop, the initial energies are defined. The forces acting on the mass, gravitational force, spring force, and the net force are all defined by their respective formulas. Newton's second law is incorporated in order to update the object's velocity and position. The equations for vector L hat, and S are inputted in order to update the spring, since the spring force changes as the mass moves. Finally, the final energies and their changes are specified. Now we will run the model and input our data from the spreadsheet into the model. And as you see, an illustration of the mass oscillating on the spring and swinging back and forth is shown. There are two graphs that are generated. One with the change in energies, which shows kinetic energy in blue, potential gravitational energy in red, potential spring energy in green, and the change in energy in orange. The other graph plots the observed position in red versus the predicted position in blue, where they are pretty much in sync with each other, but have small discrepancies due to human error and Tracker. For our what does it mean questions, the energy principle is satisfied, which states that delta E is equal to delta KE plus delta UG plus delta US is equal to 0. On our graph, delta KE, delta UG, and delta US all have non-zero values, while delta E represented by orange is 0. Then in our second question, the periods of oscillation from the X and Y position data are estimated from Tracker. The periods are slightly off due to human error in selecting the position in Tracker. Thank you.